Okay, in this video we're going to look at progress test D, and we're going to look at the first section of progress test D. So to start with then, the first question is asking us to explain which block in the periodic table sodium and magnesium belong to. So sodium and magnesium are both S block elements, and that's because their outer electron or highest energy electron is in an S subshell. Okay, so the next question is looking at the different isotopes of magnesium, and we're looking at the isotopic masses and their percentage abundance for magnesium. So we've got quite a lot of information in this question. It is worth 2 marks. Okay, so there's quite a lot to do to get the 2 marks. Okay, and there's lots of information packed up in this question. So I'm going to start off by just highlighting some of this. So it gives us the relative atomic mass, the AR of magnesium is 24.305, and it tells us that the magnesium sample consists of 3 isotopes. Okay, now that's important because only 2 isotopes are given in the table. It says that we're given the accurate relative isotopic masses and percentage abundances of 2 of the isotopes which are given in the table. So we've got isotope of magnesium 24 accurately given to 23.985, and the abundance of that is 78.99. The isotope with a mass of 25 has again got a more accurate relative isotopic mass of 24.986 and a 10% abundance. So the first thing that I'm going to do is I am going to work out the abundance of my third isotope. I don't know the mass or the accurate mass of my third isotope, but I do know that my percentage abundances need to add up to 100%. So to work out the percentage abundance of my third isotope, I need to do 100, take away 78.99, take away 10, and I get left with 11.01 as the percentage abundance of my third isotope. And then what I'm going to do is I'm going to focus on the next part of the question, which is determine the relative isotopic mass for the third isotope, and I've got to give my answer to 5 significant figures. Okay, to work out the relative isotopic mass of the third isotope, I need to use this equation, and I'm just going to sub in some information that I've got in the question. So the relative atomic mass is given, so I can say that the relative atomic mass we already know is 24.305, and that's going to equal the sum of the masses and abundance of each isotope. So that's going to be 23.985 times by 78.99 plus my mass of my second isotope, 24.986, which is multiplied by 10, plus the mass of my third isotope, which I don't know yet, multiplied by 11.01, because that's the percentage abundance of that isotope, and then divide that by 100, because my total abundance is 100. Okay? I've not got much space to work this out, but what I would do in this for the rest of this question is use some algebra to work out and isolate my M. Okay? The first thing that I would do is I would get rid of my 100 from the bottom of my equation, so I'd multiply both sides by 100. And then what I would do is I would work out all of these numbers that I've just highlighted, the bits that I can work out as a single number. Okay, if I do that, and I'm just going to write my answer that I've got so far up here. Or in a bit of space over here, let's write it a little bit over there. I would end up with 2,430.5 would equal 2,144.43515 added to my mass of my third isotope that I don't know, multiplied by 11.01. Okay, so what I'm going to do to solve this is I'm going to take away what 2,144 24.4351 from both sides, I end up with 286.06485 is equal to m times 11.01. I'm going to divide both sides by 11.01, and I end up with the mass of my third isotope, which I get as 25.9822752. So I need to give this to 5 significant figures. So my answer is going to be 25.982. Okay, so in this question, you got a mark for working out this equation, and you got a mark if you got to the correct answer and gave it to 5 significant figures. Okay, so the next part of the question is asking about calcium oxide and water. So adding calcium oxide and water in a test tube, and in a separate test tube, strontium oxide and water. Okay, so excess calcium oxide and water and strontium oxide and water to 2 different test tubes. First part of the question, write the equation for the reaction of calcium oxide with water. State symbols not required, 1 mark. Okay, so this one, we have calcium oxide plus water, and we are going to make calcium hydroxide, which is CaOH, and then 2 lots of the hydroxide in the brackets, and that's all we need to get our mark for that question. Okay, and then we get asked to suggest the approximate pH of the 2 solutions formed in the test tubes. So this really is checking whether or not you know the trend in solubility of the group 2 hydroxides, okay, which increase in solubility as you go down the group. So strontium hydroxide is going to be more soluble, or I could say that they decrease in solubility as you go up the group. So calcium hydroxide is sparingly soluble. So when it dissolves, not as many hydroxides are going to form. So the pH with calcium oxide and water is going to form, it's going to form an alkali solution. So my number of my suggested pH is going to need to be bigger than 7, and I'm going to suggest a value of 9. And then with strontium oxide, I'm going to get more hydroxides because strontium hydroxide is more soluble in water. So I'm going to suggest a pH of 13. So higher than 9, not higher than 14 though. Right, so moving on to question 2 then. We've got 3 organic compounds, A, B and C, that are labelled below. These compounds can be distinguished by simple test tube reactions. So we can tell them apart by doing some test tube reactions. For each pair of compounds, give a reagent or combination of reagents that could be added separately to each compound to distinguish between them, to tell the difference between them, and state what is observed in each case. So we start off by comparing compounds A and B. Well, the first thing to do is to try and work out the difference between these organic chemicals. So the first one, compound A, I've got the functional group C double bond O, and that's trapped in the middle of the chain of carbon atoms. So that is a ketone. The second one, I've got C double bond O again, and that's attached to carbonyl carbon has also got an OH group on it. So this one is a carboxylic acid. And the final one that we've got, compound C, we've got the C double bond O again. However, it's at the end of a chain, so it's got a hydrogen atom sticking off rather than the continuation of the carbon chain. And it's attached to a cyclic alkane. So whilst the cyclic bit looks complicated, we need to remember that actually the functional group is the same as an aldehyde. So we've got a ketone, carboxylic acid, and an aldehyde. And if you go back to the question and compare A and B, we're comparing a ketone with a carboxylic acid, and we need a reagent that's going to tell the difference between them both. So the one that I'm going to go for is one that would react with an acid, but not with a ketone. So I'm going to go for sodium carbonate, could have chosen any metal carbonate. And if I add a metal carbonate to an acid, it's going to produce carbon dioxide gas. Okay, but with the ketone, I'm going to get no change. And with B, the carboxylic acid, I'm going to get effervescence, which is the same as saying fizzing. So to score my marks in this question, I need 1 mark. I get 1 mark for the correct reagent or a correct reagent, and I need both correct observations for the reagent that I've chosen to get my second mark. So that would get me 2 marks. For the part B of this question, I need to look at compound A and C. So that's my ketone and my aldehyde. So hopefully you know that Tollens reagents can tell the difference between an aldehyde and a ketone. So with A, I would get no change. That's my ketone. And with C, I would get my silver mirror. And the mark scheme's the same for this one. So I get 1 mark for a correct reagent, and I get another mark for both of my observations being correct. So I get 2 marks for that. Okay, so moving on to look at question number 3. This question is about the first ionization energies of the elements in period 2 and how the first ionization energy changes as the atomic number increases. So we've got to explain the pattern in first ionization energies of the elements from lithium to neon. So period 2 is the second row of the periodic table, so that's lithium to neon. And this is a 6 marker. So 6 mark questions are normally worth you spending a bit of time thinking about what it is that you're going to say. So I've got to explain the pattern in the period 2 elements, and I'm going to start off by just thinking about the general trend. So if you remember this graph from A1, we've got a general trend that increases as I go from left to right, as I go from lithium through to neon. Okay, so I need to be able to say what that trend is, that the first ionization energy increases. So that goes up, and I can say that is because each time I move across from lithium, beryllium, boron, etc., I'm going to get 1 more proton in the nucleus. My atomic number increases, so my nuclear charge is going to increase. And I can say that my electrons are in the same shell. So I'm going to get a similar shielding. And that means that my outer electron is going to be attracted more strongly to the nucleus, and it's going to take more energy to remove it. Okay, so I can explain that general trend. But to get 6 marks, I need to try and explain these 2 little dips in the graph. So that's between beryllium and boron, and nitrogen and oxygen, so group 2 and group 3 and group 5 and group 6. So to do that, I'm just going to remind you of boron's and oxygen's electron configuration. So boron is 1s2, 2s2 and 2p1. So I'm just going to put this on in my energy profile diagrams. So if I'm putting my electrons, pairing them up, boron is the first time across period 2 where I get an electron in the 2p orbital, and the 2p orbital is slightly higher energy than the 2s orbital. So I can explain that dip from beryllium to boron because it's the first time my electron is in a 2p orbital. Okay? And if we move on and have a look at oxygen, we've got oxygen's electron configuration as being 1s2, 2s2, and this time we've got 2p4. So those first 3 electrons are unpaired. That 4th electron is forced to pair up. Whoops. So that forms the first pair of electrons in the 2p orbital or subshell. So that explains why there's something different going on with oxygen, and that pair of electrons together repel each other, meaning that they're slightly higher energy, and it's easier to remove a paired electron than an unpaired electron. Okay, so if we look at a good answer for this question, so I've written in the first part of an answer. So we've got the general trend, which is that the first ionization energies increase as we go across the period from lithium to neon. Now, this in the mark scheme would get you mark 1A, so this is marked in levels or stages. So the first stage being level 1 or stage 1. So that gets you one of the marking point, not necessarily one mark, but one of the marking points, okay? So we need to say that there's an increase in nuclear charge or an increase in protons every time. So that gets you marking point 1B. If we say that the outer electrons are in the same shell, so there's similar shielding, that gets us marking point 1C. And then we are saying that there is more energy required to remove the outer electron as it has a stronger attraction to the nucleus. That gets us marking point 1E. What I said before, for the outer electrons in the same shell, that gets 1C, and 1D is that there's similar shielding. Okay, so at the minute, we've only got marking points in stage 1 or level 1 of our answer. And unfortunately, if you've only got level 1 or stage 1, even if you've got all of those points, you're just going to limit yourself to a maximum of 2 marks. Okay, so to score highly in this question, we need to access the other stages. Okay, so again, I've written some answers for these here. I'm just going to pop onto the page there. Okay, so stage 2 or level 2 is explaining the trend from beryllium through to boron, beryllium to boron, and to start with this, okay, there's only three marking points, and they correspond to my 3 bullet points with this. So I've said that boron has got a lower first ionization energy than beryllium, so that's marking point 2A. And that's because, remember that boron's outer electron is in a 2p subshell, and that's the first time that happens. That's 2b. And I need to say that it's a 2p subshell. I've got to get that bit right if I'm going to name the number of the subshells. So if I put 3p there by mistake, I'm not going to get that marking point. I can get away with p subshell, but if I'm going to put a number in front of it, I've got to get the number right. And then the third marking point in stage 2 is that the 2p subshell is higher in energy than the 2s, and that's going to mean that there's less energy required to remove that electron. So that gets me marking point 2C. And again, if I've got stage 1 and stage 2, that's going to limit the number of marks that I can get, so I can get up to a maximum of 4 marks now. Unless I've said something in stage 3, and stage 3 is talking about the difference in first ionization energies between oxygen and nitrogen. So we might expect oxygen to have a higher first ionization energy, but it doesn't, and that's because oxygen's got the first pair of electrons in the 2p subshell, and the paired electrons repel, and so take less energy to remove than an unpaired electron. So my bullet points here correspond to marking point 3A, 3B, and 3C. So to get 6 marks or to access full marks in this question, you need to get the majority of each stage correct. Okay, so that's 3 out of 5 of my first 5 marking points, minimum of 2 out of 3 of my second lot of marking points, and a minimum of 2 out of 3 of my third set of marking points. Okay, and you've got to have accurate information in there. So this answer would get 6 marks, but you've got to think, actually, have you explained something in each of the stages as fully as you can? Okay, so moving on to question 4 then. So this question is about some group 7 compounds, and we're going to start off with solid sodium chloride reacting with concentrated sulfuric acid. We need to give an equation for the reaction and state the role of the sulfuric acid in the reaction. So I'm going to start off with the equation sodium chloride plus the sulfuric acid. And if you remember this from group 7, this is where we're going to form sodium, hydrogen sulfate, and hydrogen chloride gas, and we'd get misty white fumes of hydrogen chloride gas. Now, in these type of reactions with sulfuric acid, the sulfuric acid is either going to behave like an acid, or it's going to behave as an oxidizing agent. And in this reaction, the sulfuric acid hasn't behaved like an oxidizing agent because the chlorine in sodium chloride has got an oxidation state of -1, and it's still -1 in hydrogen chloride. So the sulfuric acid isn't strong enough an oxidizing agent to take the electron away from the chlorine. So in this example, the sulfuric acid isn't an oxidizing agent, but it is donating a proton, so it is behaving like an acid. So we can say it's behaving like its role as an acid, or we could have said it's a proton donor. Okay, so 1 mark for each of those to get us 2 marks for that particular question. And we're moving on to the part B. So we get fumes of sulfur dioxide when sodium bromide reacts with concentrated sulfuric acid. And this time we've got to give an equation, give one other observation, and state the role of the sulfuric acid. And this is 3 marks. So we're going to get 1 mark for each of those 3 things. I'm going to start off with the equation, but I'm not going to write the overall equation straight away. I'm going to write a half equation for when the sulfur dioxide is formed, and that's going to form from the sulfur in the sulfuric acid. So I'm going to write a half equation to show what's going on, because this is a redox reaction, because the sulfur in sulfuric acid has an oxidation state of +6, and in sulfur dioxide it's +4. So the sulfur has been reduced, it's gained some electrons. Okay, and before we find out where those electrons have come from, we're going to balance this equation, because at the minute it's imbalanced. We've got hydrogens and oxygens that we need to sort out. And I'm going to start off by balancing the oxygens on the right hand side, and to do that I need 2 more oxygens, so I'm going to use water to provide those 2 oxygens. And then I've now got an imbalance of hydrogens. I've got 4 hydrogens on the right hand side. I need 2 more hydrogens to make 4 hydrogens on the left hand side. And now my charges aren't balanced, and my charges need to get balanced. So I need to show that the sulfur in the sulfuric acid has gained 2 electrons to go from +6 to +4. So I've got a half equation for that reaction of forming sulfur dioxide, but I need to know where those electrons have come from, and they are going to have come from the bromide in sodium bromide. And when bromide loses electrons, it's going to form into bromine, and I need 2 electrons, so I'm going to have 2 bromides forming Br2, and I'm going to form 2 electrons as well. So now I've got the other half of that redox equation, and what I can do now is I can put them together, and quite handily what I've also done is I've got my other observation, which is I'm going to form orange fumes of bromine. But let's put these 2 things together. So I'm going to combine these 2 half equations, and I am going to cancel out the 2 electrons because they're going to appear on both sides. So my overall equation is going to be 2H plus my sulfuric acid plus 2Br minus, and that's going to make my bromine plus my sulfur dioxide plus my 2H2O. I'm just going to put a line through my half equations because I want the examiner to mark the equation that I've just written. So that is going to be worth 1 mark. And my observation is that I'm going to see orange fumes. And that's when the bromine is being formed. And this time, my sulfuric acid is behaving as an oxidizing agent, because it is removing electrons from the bromide to form bromine. So 1 mark for each of those 3, and I can move on. So okay, the next question is chlorine reacting with sodium hydroxide, and we form 2 products with chlorine in it: sodium chlorate, NaClO3, and sodium chloride. And the first thing we've got to do is give the oxidation state of the chlorine in sodium chlorate and sodium chloride. So I'm going to start with the sodium chlorate. So I'm going to use oxygen and sodium's oxidation state to work out chlorines. So I've got 1 sodium, so an overall +1 charge. I've got 3 oxygens, which are -2, so I've got a -6 coming from the oxygen. That must mean that the chlorine is bringing +5 to that and has got an oxidation state of +5 because there's only 1 chlorine in there. And in sodium chloride, it's much simpler. We've got +1 for sodium, -1 for chlorine, so -1 as the oxidation state there. Okay, and we've got to then state in terms of redox what happens to the chlorine in the reaction. Well, the chlorine starts off with an oxidation state of 0 because it's in its elemental form, and goes to +5 in sodium chlorate and -1 in chlorine. So it is both being oxidized and reduced, and that's an example of a disproportionation reaction. So we would get 1 mark for getting both of these oxidation states correct, and 1 mark for getting either by saying oxidized and reduced, or 1 mark for saying disproportionation. Okay, so the question carries on the next page. So we've got something that the exam board have made a little bit complicated by adding in lots of letters, and we've got a table to interpret as well. So I'm going to try and break this down and try and simplify what is going on here. So let's just look at the information in the question. We've got solution Y, and we get told that it contains two different negative ions. And a student is going to add to solution Y silver nitrate solution, then an excess of dilute nitric acid, and then lastly an excess of concentrated ammonia solution. And we get some observations after each addition in the table. So we've got the silver nitrate, then the excess nitric acid, and the concentrated ammonia. And what we've got to do before we look at the observations, we're going to look at what we've got to do, and we've got 6 marks available here. We need to try and work out the formula of D, E, and F. So these are the letters that we get given in the table above. And we need an ionic equation to form E. And we need to have an equation for the conversion of D into G. Okay, so we've got to give all of these things. And to do that, we've got to work out what's gone on using the observations in the table. So firstly, let's just concentrate and have a look at when we add the silver nitrate solution to our remember they're 2 different negative ions. So we get something going on when we add silver nitrate. Now, just to break this apart a little bit, silver nitrate is made up of silver positive ions and nitrate minus ions. So when we're going to add this to our solution of Y, it's going to be the positive silver ion that is going to form the compounds D and E. So it's going to be, both compounds are going to be silver and then whatever the negative ion is. Okay, one observation is that we get a cream precipitate. So you've got to bring some knowledge to this, and you've got to bring the knowledge that silver nitrate reacts with the halide ions to form different coloured precipitates, and the one that forms the cream precipitate is bromide. So this one's going to be silver and bromide. Okay, so that's compound D, so let's put that in there. We've got silver bromide, already one of those ticked off. Compound E, we've got no observation, we've got nothing to identify compound E yet, other than it's going to be silver as a positive ion and our mystery negative ion, whatever E is made out of. Let's move on, let's try and find out some more information. So if we add some nitric acid, we still get the cream precipitate, that's silver bromide, still there. So that's no good to us in terms of information. And we get bubbles of gas F. Okay, so we've got a negative ion that when we add an acid to it forms bubbles of gas. Okay, so we've got to identify what those bubbles of gas would be. So I'm going to say that the negative ion is going to be a carbonate ion, and that bubbles of gas, gas F, is going to be carbon dioxide. So that's the negative ion that's going to produce a gas. The one that we know about is the carbonate ion. So the bubbles of gas F are going to be carbon dioxide. So let's put that in there. And then what we're going to do is we're going to just work out the formulae of our silver carbonate, because remember it's going to be the silver that's going to form the compound E with the negative carbonate ion, and because carbonate is 2-, I'm going to need 2 silver ions to do that. So I'm going to need to have Ag2 CO3 for the formula of my silver carbonate. So I've identified D, E and F. I need to write an ionic equation to form E. So I'm basically going to do what I've written around the table, in that I need 2 silver ions for every carbonate ion, and that's going to form my silver carbonate. Okay, so these first 4 things that we've done each get us 1 mark, so 4 marks out of the 6 so far. And the last thing that we've got to do is to write an equation to show the conversion of D into G. So D, remember, is our silver bromide. So let's have a look at the last reaction on here. We add excess concentrated ammonia solution and we form a colourless solution. So our cream precipitate has disappeared. We get a colourless solution containing complex ion G. Okay, so if you remember your reactions of your group 7 halide ions in solution, you'll know that it's the bromide ion that will disappear or dissolve into the solution when you add excess concentrated ammonia, and the iodide ion won't, and that's one of the further tests that we can do to tell the difference between a cream or a yellow precipitate of the iodide. So what's happening here chemically is that the bromide, the silver bromide, is reacting with the ammonia and it forms a complex ion, and the complex ion is a silver ion with 2 ammonias surrounding it at each end of it, and we release the bromide ion into the solution. So we need to put a 2 in front of that NH3. And the mark scheme for this, there's 2 marks available. There's 1 mark if you got the correct formula of the silver ion, the silver complex ion, and there's another mark for the correct equation that's balanced. So 6 marks in total. Okay, so question 5 then. We've got an ion, H2F+, and that's formed when hydrogen fluoride gains a proton, as shown in the equation. Okay, so we've got to name the type of bond and explain how this bond is formed, and it's worth 2 marks. So this bond is formed because the hydrogen is electron deficient. It's hydrogen ion, it doesn't have any electrons in its outside shell. And the fluorine has got 3 lone pairs of electrons. So I'm going to form, or the fluorine is going to be able to form, a coordinate or a dative covalent bond. So I could use either term. And we need to explain what a coordinate or a dative covalent bond is. And that is where both electrons in the bond have come from, in this case, the fluorine. So we get 1 mark for the name of the bond and 1 mark for saying how a coordinate bond is formed. And then we've got a question about shapes. So we've got fluoroantimonic acid, and it contains the 2 ions, SbF6- and H2F+. We've got to draw the shape and name the shape of each of these ions. And we've got to include any lone pairs of electrons that influence the shape. So, first thing to do with this is to identify the central atom. So we'll start off with Sb6-. So Sb is in group 5 of the periodic table, so it's got 5 electrons in its outside shell. But there's a negative charge on the ion, so I'm going to add an extra electron to that. So I've got 6 electrons and I've got 6 fluorines. So I'm going to form 6 bonded pairs of electrons, and I've got no electrons left. So I've got 0 lone pairs, 6 bond pairs, 0 lone pairs, and something with 6 bond pairs and 0 lone pairs is going to be based on the octahedral shape. So I'm just going to draw that in, and I'm going to put my fluorines on the end of my bonds, and I've got to remember that this has got a charge, so I'm going to put some square brackets on the charge on the outside of that bracket, and this is octahedral. And my second ion, H2F+, so my central atom is going to be fluorine. Fluorine's in group 7, so it's got 7 electrons in its outside shell, but I've got a positive charge on the ion, so I'm going to take away an electron because fluorine has got the whole ion has got a positive charge. So I'm going to go down to 6 electrons in my outside shell. 2 of those electrons from around the fluorine are going to be involved in covalent bonds with the hydrogen. So I'm going to get 2 bonded pairs. That leaves me with 4 electrons left over, and those electrons are going to pair up and form lone pairs. So I'm going to get 2 bond pairs, 2 lone pairs, and that shape is the same shape as water. So my lone pairs that I need to include, because the question has asked me to include my lone pairs, I'm going to put on the fluorine atom, and my shape is going to be V-shaped, or I could say angular, or I could say bent, and I've got to remember that this also is an ion, and so I'm going to put the charge on the outside of the square brackets. So I'll get 1 mark each for each shape. The lone pairs on the fluorine on the second shape are important. They need to be there and included in that. And I get 1 mark for the name of each of those shapes. Okay, moving on then. So we have got a question about bond enthalpies. So we've got hydrogen fluoride reacts with ethyne as shown in the equation. All compounds are in the gaseous state. And we've got some bond enthalpy, mean bond enthalpy data in the table, and we've got an enthalpy for the reaction. So we've got to use the data in table 1 to calculate a value for the bond enthalpy of the carbon-fluorine bond. So we don't have that data in our table. We've got all of the other bond data, so we've got all of the CH bonds. There's 2 more there. We've got the carbon-carbon triple bond in ethyne, the hydrogen fluoride bond, and we've got the carbon-carbon bond. Okay, so what we need to do for this question is we need to remember that the enthalpy change for the reaction is equal to the sum of the bonds broken, take away the sum of the bonds made. Okay, so what I'm going to do is I'm just going to sub in what I know. So the enthalpy change for the reaction is -179, and I'm going to say that is equal to the sum of all of the bonds that I'm going to break, and I'm just going to go through this methodically, so I'm not going to miss any of these bonds in here. So I've got my carbon-carbon triple bond, that's 837. I've got then 2 lots of 412, they're my 2 carbon hydrogen bonds on my ethane, and then 2 lots of 562, that's my 2 lots of hydrogen fluorides. I'm going to add all of those together, then I'm going to take away the sum of all the bonds that I'm going to make. So 4 lots of carbon and hydrogen bonds, that's on my molecule that I've made. And finally, I've got my carbon-carbon bond, which is 348. And then the 2 bonds that I've highlighted in purple, the bond enthalpies that I don't know, I'm going to sub those into my equation. Okay, so what I'm then going to do is I'm going to simplify a little bit. So I'm going to add all of those together. I get 2785. I'm going to add all of these ones together. I get 1996. And then I'm going to rearrange this equation. So I'm going to take away. I'm going to add 1996 and my 2 carbon fluorine bonds to both sides to get rid of them from the right hand side. And then I'm going to get rid of my 179 by adding negative 179 by adding it to my 1996, and then I'm going to take away 1817 from both sides. That gets me with my 2 carbon fluorine bonds equaling 968. I'm going to divide both sides by 2, and that gets me a bond enthalpy of 484. So just before I confirm this as my answer, I'm just going to check with the data in the table and what I know about bond enthalpies. It looks like it's in the right order of magnitude. It looks like it's about the right size, and it's a positive number, which is important because bond enthalpies are always endothermic because they require energy to break. So I think I've got a good, reasonable answer for that particular question. Okay, so question 6. We've got a question about propene reacting with concentrated sulfuric acid, and we get 2 isomers, isomer E, isomer F, and we get given the structure of isomer E. So we started off with propene, and we've added sulfuric acid, or we've added hydrogen sulfate to it, rather, I should say. And what we've got to do is to name and outline a mechanism for the formation of E in this reaction. So this is worth 5 marks. Well, when we start off with an alkene and we add something to it, the name of the mechanism is electrophilic addition. So that's going to get us marking point number 1 of this particular question. What we've got to do in this question is we've got to draw the mechanism to show the formation of isomer E. So we want to add our hydrogen sulfate to carbon atom number 2. But just before we do that, I've drawn down at the bottom the structure of sulfuric acid, and I've just highlighted, I'm going to highlight this part of the sulfuric acid because that's the part that I'm really interested in, is the hydrogen and oxygen bond and the partially positive hydrogen, the partially negative oxygen. And I'm just going to simplify the structure of sulfuric acid so that all I really want to do is I want to show this particular bond, because this is the bond that is involved in all of the action in the mechanism. So what I'm going to do is I am going to write the rest of the formula for this. So first the S, then the 3 O's, and then the H. So I'm going to write that as S, then the 3 O's, and then the H. So I'm going to write my sulfuric acid in a simplified form to the right of my overall structure, so that it makes it easier for this mechanism. So I'm going to draw out up here my propene molecule. So I'm going to have CH3 and then CH and then C double bond, because that's my carbon-carbon double bond of my propene, and then CH2 at the end. And I'm just going to position my electrophile close to where the double bond is, because it's going to be the double bond that is going to attack the electrophile. Okay, so the electrons are going to come from the double bond and they're going to attack the partially positive hydrogen, and that's going to grab onto that hydrogen and form a covalent bond, and then the oxygen and hydrogen bond is going to break, and both electrons in the bond are going to go to the oxygen. Okay, so I would get marking point 2, marking point 3 for both of those curly arrows that I've just drawn, and I would form an intermediate. So I'm going to have CH3, C, same H as before, and then this time I've only got 1 carbon-carbon bond there because I've just added on a hydrogen atom, and I'm going to add it on to this end carbon atom here, and I'm going to draw it in pink so that you can see that that's the hydrogen that's come from the sulfuric acid, and I've added it on there because I want to form a carbocation on the middle carbon atom, because that's where the rest of my sulfuric acid has been added onto. So I'm just going to draw what's left of the sulfuric acid, or the hydrogen sulfate ion. So that's OS, O3H, and that oxygen at the end, remember, has got both the electrons in the bond from the oxygen and hydrogen bond that broke before, and it's going to have a negative charge. So it's a hydrogen sulfate ion, and I would get a mark for the correct structure of my carbocation. So that's marking point number 4. And then my 5th marking point comes from the final curly arrow, where I add my hydrogen sulfate onto the carbocation that I formed. So that's marking point number 5. And I'm just going to finish this mechanism by drawing the final structure that I would make. And my hydrogen sulfate added to that middle carbon atom. Okay, so if we then go on, we've got to draw the structure of F, which is our other isomer that we could form. Okay, now what we could have done when we formed the carbocation from before, if I just come back up here, we could have attached the hydrogen onto the middle carbon atom and formed our carbocation on the end. And if we'd have done that, our hydrogen sulfate would have attached onto the end carbon atom. So that's going to be the structure of F. So let me just draw that out. So I'd have my CH3. I'd have my carbon and hydrogen. I'm just going to add the hydrogen that I added to the end carbon atom before in pink into the middle one. So change its position just so you can see that's where it's attached onto on this one. And instead of CH3 at the end, I'd have CH2 and then my hydrogen sulfate attached to that end carbon atom. So that's my isomer F. And we've got to explain why more of isomer E is formed than isomer F in this reaction. Well, that's because we would either form a secondary carbocation or a primary carbocation. What we need to do is we need to say that E is going to be the major product that's formed because E is come from a secondary carbocation, F was formed from a primary carbocation, and we know that secondary carbocations are more stable than primary carbocations. For 1 mark for each of those marking points and 1 mark for our correct structure of F. Okay, moving on to question 7. So this question is about some compounds with different molecular formulas but have the same relative molecular mass. And we start off with a dicarboxylic acid with a relative molecular mass of 118, and we've got to deduce the molecular formula of the acid. So this is worth 3 marks. Okay, so we should be able to do this given the information in the question. So let's just have a look at what we've got. We've got a dicarboxylic acid. So I'm just going to draw out the carboxylic acid group, C double bond O and OH. And I'm going to start off by trying to work out what the mass of that is. But whilst I'm doing that, I'm going to draw in the second carboxylic acid group as well, because we've got 2 of them. So if I work out the relative molecular mass of those 2 carboxylic acid groups, let's see what I've got. I've got 2 oxygens, so 2 lots of 16. Add carbon, which is 12. Add hydrogen, which is 1. That gets me 45. I've got 2 lots of those, so that comes up to 90. I am missing 28 to get me up to 118, which is the relative molecular mass from the question. So I need 28. I need a mass of 28 more to add to this. So I'm just going to try and add some carbon and hydrogens. If I add a CH2 group, that adds on an extra 14. And if I add another one, then quite handily, I've now get up to 118. So I've got something that's plausible for my structure of my dicarboxylic acid. But I've got to remember that I've got to come up with a molecular formula and not the structural formula, because what I've drawn at the minute is a bit of a mix of structural and displayed formula. So the molecular formula is just a simplified version of that. So that's going to be 4 carbons and 1, 2, 3, 4, 5, 6 hydrogens and 4 oxygens. So I'll put a line through that. So I want the examiner to mark my molecular formula that I've written out. Okay, so the question then moves on and looks at a titration. So this is where a student has dissolved some of the dicarboxylic acid from part A in water and made up the solution to 250 cubic centimetres in a volumetric flask. And they've taken 25 cubic centimetres of that and they've titrated against sodium hydroxide, and they needed 21.6 cubic centimetres of 0.109 mole per cubic decimetre of the sodium hydroxide solution for neutralisation. So we have got to calculate the mass in grams of the dicarboxylic acid used and give your answer to the appropriate number of significant figures. Okay, so this is worth 4 marks, and it is a case of taking it step by step and just going through and working out methodically what it is that you can do. So the first thing that I'm going to do here is I'm going to work out how many moles of sodium hydroxide I had in my titer value of 21.60 cubic centimetres. So to do that, I'm going to use the concentration equation, N equals C times V. So my concentration is 0.109 that I've got from the question, and my volume in cubic decimetres is 21.6 times 10 to the minus 3. That gets me 2.3544 times 10 to the minus 3 moles of sodium hydroxide. And this is where I've got to be a little bit careful, because for every mole of sodium hydroxide that I get, I'm going to react it with half the number of moles of my acid, because my acid is a dicarboxylic acid. So every mole of my acid is going to donate 2 protons. So for every mole of sodium hydroxide, I'm only going to need half a mole of my dicarboxylic acid. So to work out the number of moles of my dicarboxylic acid, I'm going to divide the number of moles of the sodium hydroxide by 2 to get the moles of acid in that 25 cubic centimetre portion. So for working out the moles of sodium hydroxide, you would get 1 mark. For dividing by 2 and getting the moles of acid in the 25 cubic centimetres, you get the 2nd mark. Once I've worked out the number of moles of acid I've got in 25 cubic centimetres, I then need to remember that the student made the volumetric solution up to 250 cubic centimetres, but only titrated a tenth of it, and they only titrated 25 cubic centimetres. So I've got to multiply the number of moles of acid in 25 cubic centimetres by 10 to get the number of moles that I originally had in my volumetric solution of 250 cubic centimetres. So I get another mark for doing that by multiplying by 10. And then finally, going back to the question, I need to calculate the mass in grams of the dicarboxylic acid used. So to do that, I need to use my equation down here, mass equals Mr. moles, the relative formula mass times the number of moles. And the relative formula mass is 118. We get told that from up here in the question. And we need to times the relative formula mass by the number of moles, 1.177 times 10 to the minus 2. That gets us a mass of 1.38886. Okay, and that would be grams. And the final thing that we've got to do is we've got to remember we've got to give that to the appropriate number of significant figures. So if I look at my question, I have got numbers given to 118 is 3 significant figures, 250 is 3 significant figures, 25.0 is 3, 21.60 is 4, 0.109 is 3 significant figures. So I'm going to go with the smallest number of significant figures given to me in the question, which is 3. So I'm going to give this to 3 significant figures. So the answer is going to be 1.39 grams to 3 significant figures. And that gets us the 4th and final mark for that particular question. Okay, question 8. So in this question we've got 3 alcohols A, B and C that are structural isomers of C4H10O. And here they are, A, B and C. And each alcohol is refluxed with acidified dichromate And what you've got to do is draw the structures of the organic products, and if there's no reaction, write none. So this question is about the oxidation of alcohols, and if you have a look at the three alcohols that we've got a alcohol A is a primary alcohol, alcohol B is a tertiary alcohol, and alcohol C is a secondary alcohol. So this question is really about that. Do you know what happens when you oxidize primary, secondary, or try and oxidize tertiary alcohols? So a primary alcohol, if it's oxidized and it's refluxed, then it's first of all going to turn to an aldehyde, and then eventually it's going to turn to a carboxylic acid. And because it's reflux, that's the product that we need to form. So I'm just going to draw in what this structure is going to look like. So we've still got that OH group, and then we've got the C double bond O sticking up at the top there. The tertiary alcohol isn't going to be oxidized because we can't form a double bond O on that carbon atom in the middle, because it's already got too many, well, it would have too many bonds if it did. So this one is going to be no product is going to be formed. And then for C, we are going to oxidize the alcohol. And again, if I just draw this structure, I'm going to have my C double bond O sticking out from that carbon atom there. Now I've got to give the IUPAC name for alcohol C. So alcohol C is going to be based on a carbon chain, the longest carbon chain, 4 carbon atoms, and the alcohol is on carbon atom number 2. So 1, 2, 3, 4. So this is going to be butan 2-ol. And then we've got to give an equation for the complete combustion of alcohol A. So C4 H10O plus oxygen, that's going to make 4 carbon dioxides, and we're going to need 5 waters. So I need to count up the oxygens on the right hand side. So I've got 5 from the water, and I've got 8 from the carbon dioxide. That gives me 13. I've got to be careful here not to put 6.5, because I've got to remember there's an oxygen there. So I just need 6 oxygens, 6 O2s, and then the extra 13th oxygen comes from the alcohol. So let me just rub that out. Okay, so moving on to the last part of this question, we've got a question about butane reacting with chlorine by radical substitution, and we're going to make a mixture of organic compounds, including this one here, with just 1 hydrogen being removed, 1 chlorine being attached, and compounds D and E a little bit later on. So we've got to complete the table to show the mechanism for the initiation and propagation stages of the reaction with butane with chlorine to form this product here. We've got to use, in your equations, use molecular formulae. So we've got to stick with molecular formulae. We've got to use dots for any radicals. Okay, so to start with, we're going to use chlorine to form our chlorine radical. So this is going to be the initiation. We're going to take a chlorine molecule and form 2 chlorine radicals with a radical dot on the chlorine. And the conditions that we need is ultraviolet light. So the propagation reaction, we're going to take butane in its molecular formula, and we're going to take one of the chlorine radicals that we just formed, and we're going to take off a hydrogen from that to form hydrogen chloride. So we're going to have C4H9, and we're going to form a radical, and the radical would be on one of the carbon atoms, but it doesn't actually matter where you put this on the in the mark scheme, because we're using molecular formulae. And then I'm going to take the radical that I've just formed on that carbon, on what used to be butane, and I'm going to take another chlorine molecule, and this time I'm going to attach a chlorine onto what was the radical, and by doing that it means that I've split the chlorine molecule in half and I've formed another chlorine radical. So I've got two propagation reactions there, and I've completed the table. So I'm then going to move on to the last question. Organic compound D is formed by substitution of all the hydrogen atoms in butane. So I'm going to take all the hydrogen atoms off butane and by chlorine atoms. So I'm going to replace all the hydrogens with chlorine atoms. I've got to write an equation for the formation of D from butane, use molecular formulae. So I'm going to make something with 4 carbon atoms and 10 chlorine atoms, okay? So each time I take off a hydrogen, I am forming hydrogen chloride. And because I've taken off 10 hydrogens, I'm going to need to form 10 hydrogen chlorides. So I started with butane, and I reacted it with chlorine, which formed my radical, and I need 10 molecules of chlorine because I need 20 chlorine atoms. That is the equation that we need to form compound D. Okay, so that is the end of the first part of Progress Test D, and thank you for watching.